Hello, good day everyone. So welcome back to my YouTube channel, and today we will be talking about testing the difference between two variances. So introduction, if two independent samples are selected from normally distributed population in which a population variances are equal, if the samples variances are compared, the sampling distribution is called the F distribution. So if we're going to compare two variances or sampling distribution of the variances, that is what we call as the F distribution. So the F test formula is given by F is equal to the variance 1 over the variance 2. Sample variance 1 over sample variance 2. Where S2 1 is the larger, or variance 1 is the larger two of the two variances and is placed in the numerator. Take note, the larger of the two variances is placed in the numerator, and the variance 2 is the smaller variance. This is true regardless of the subscripts. So the f-test has 2 degrees of freedom. Numerator is n1, n sub 1 minus 1, where n1 is the sample which the larger variance was obtained, and n2 is the sample of which the smaller variance was obtained. So we have here the characteristics that we need to know, that in this f-test or this f distribution, so the first one is non-negativity. F values cannot be negative because variances are always positive or zero. So take note, F values cannot. Okay, non-negativity, F values cannot be negative in an F distribution. Positive skewness. Okay, positive skewness is positively skewed. The distribution is positively skewed. Same way here, this one. So the mean value of f is approximately equal to 1. And the fourth one is that in family of curves, the f distribution is a family of curves each defined by the degrees of freedom of the variance in the numerator and degrees of freedom of the variance in the denominator. So testing hypothesis in the testing the equality of two variances. So we have to take note of this one. This is our when HO is equal to population variance 1 is equal to population variance sub 2, and our H1 or alternative is this one, population variance 1 is greater than population variance 2. So if that is a left-tailed, so this is lesser, and if this two-tailed, that is not equal to our alternative hypothesis. So we are not talking about variances. Um, variances. So there are four key points and assumptions of using f-tests. The first one, the larger variance should always be placed in numerator and formula regardless of the subscripts. For two-tailed tests, the alpha must be divided by 2. So take note of this one. The alpha must be divided by 2, and the critical place on the right side of the f-core. So that is the right side of the f-core. The critical value placed on the right side of the f-core. So that is placed in the right side of the f-core. And of course, so the standard deviations, instead of the variance given a problem, they must be squared for the formula for the f-test. You have to square if they're given a standard deviation. When the degrees of freedom cannot be found in table H, we have here table H, the closest value in the smaller side should be used when you're using manual. Unlike when you're using software, it will be given. It will just be coded, or it will just be programmed or by point click. So assumption for testing the difference between two variances. The first one is a sample must be random samples, and the population from which samples were obtained must be normally distributed. The test should not be used when the distribution depart from normality. So if that's not normal, depart from normality, so the test should not be used. The sample must be independent of one another. So these are the assumption in testing the right between two variances. We need to follow this. Okay, we have to understand. Okay. So let's have problem number 1. Find the critical value of the right-tailed f-test when alpha is 0.05. The degrees of freedom of the numerator abbreviated by DFN are 15, and the degrees of freedom of the denominator DFD are 21. Sorry, I have a cap now. Okay, so we have to take this one since the given is degrees of freedom already, so we'll not subtract it by 1. So here, the degrees of freedom given in the f-test table H, that is f, and we are talking about alpha here. Our alpha is 0.05. So if the degrees of freedom of numerator, this is numerator, and denominator is 21. So we will have 15 here going to 21. So therefore, our critical value, okay, in this case, the critical value is equal to 2.18. So that would be our critical value. Okay, so next one is problem number 2. Find the critical value for two-tailed f-test when alpha is equal to 0.05. So when it is two-tailed, we have to divide it by 2. Okay, so when the sample size from the variance of denominator was obtained was 21, and the sample size so the variance of denominator was obtained was 12. So take note that is alpha is equal to 0.05, so we have to divide it by 2. So alpha divided by 2, 2 refer in the table. So 0.05 divided by 2, that is 0.025. So the alpha that we're going to refer in the table is 0.025. And since the sample size is given, not the degrees of freedom, so dfn is equal to 21 minus 1, that is equal to 20. Our dfd is equal to 12 minus 1, that is equal to 11. So if we're going to look at that one using this 0.025, our dfn here is 20. Okay, numerator and paired with 11. Okay, this one, 3.23. So therefore, our critical value for this case is 3.23. So that's here. That's it on how to find the critical value using F table H or F distribution. Okay, let's proceed with problem number 3. A medical researcher wishes to see whether the variance of the heart rates in beats per minute of smokers is different from the variance heart rates of people who do not smoke. 2 samples are selected and the data are shown here. This one. At alpha 0.05, is there a significant difference to support the claim? Assume that variable is normally distributed. So we have to take note that that this should be normally distributed. So step number 1 is we have to state the null hypothesis or state the hypothesis and identify the claim. So our HO, variance 1 is equal to variance 2. And our H1 here is variance 1. So the researcher wishes to see whether whether the variance of the heart rates is different. The word is different mean to say it's not equal to variance 2. which is our claim. Okay, next step is we need to find the critical value. Step number 2, we need to find the critical value. Since the alpha, this is two-tailed test here, so we have to divide it by 2, the 0.05 divided by 2, the 0.025. Our DFN, so our DFN is equal to 26 minus 1, that is 25. The greater variance, our numerator, our DFD is equal to 18 minus 1, that is 17. So if we're going to locate this one, 26 minus 1, 25, we cannot see 25 here, but the nearest value for this one is 24 and 17. That is 2.56. So therefore, the critical value here is 2.56, equal to 2.56. Step number 3. So we have to compute the test value. Okay, to compute the test value, F is equal to numerator, the larger variance over the smaller variance. So the larger variance here is 36. And the smaller variance is 10. That is 3.6. And step number 3, we have to decide whether to reject or accept the null hypothesis. Okay, so we are going to graph. Okay, graph. Okay, that's positively the property for this one. So we have to take note that is the distribution is positively skewed. Like this, that is positively skewed. Okay. Okay. Okay, positively skewed here. That is skewed to this part. Okay, skewed. And we have to write the critical value to the right. So this is this one, 2.56 to the right. So our, in this case, this is 2.56. So that's greater 3.6. So here, in this case, there is 3.6. So therefore, we could say that we have to reject the HO since 3.6 rather, 3.6 is greater than 2.56. So we have to reject because that is part of the rejection region. So that is 2.56. 3.6 is greater than 2.56. And step number 5, so if our claim is our H1 and we reject the null hypothesis, we will start with the conclusion as or summary as there is enough evidence to support the claim that the variance of the heart rates of smokers and non-smokers is different. So that's it on how to solve problem number 3. Let's proceed with problem number 4. Okay, so let's proceed with now problem number 4. The mean noise level of random sample of 16 riding power mowers is 93.2 decibels. And the standard deviation is 4.3 decibels, while the mean noise level of random sample of 12 push power mowers is 89.5 decibels. and the standard deviation is 3.6 decibels. Is there enough evidence at alpha 0.01 to conclude that the variance of the noise levels of the riding power mowers is greater than the variance of the noise levels of the push mowers, power mowers? Assume that the noise levels of both types of power mowers are normally distributed. So take note that it's normally distributed. And the more is greater than the variance of the noise of the level push power mowers. So that is our claim. So our step number one, we have to state the hypothesis. So our HO is this one is not equal to our variance 2. And our claim is our H1 since stated as greater than the variance. So the variance 1 is greater than the variance 2, which is our claim. Step number 2. Step number 2, we have to find the critical values. So given here, we have here our DFN. So our DFN is 16 with the standard deviation is 4.3. And the other one is 12 and the standard deviation is 3.6. So you have to square this because the given is standard deviation. So therefore, our DFN is 16 because 4.3 and the other one is 3.6 only. So we have here 16 minus 1, that is equal to 15. So we have to square. And our variance 1 is equal to 4.3 squared. Our DFD is equal to, we have 12 minus 1, that is 11. Our variance 2 is 3.6 squared. So now what is the critical values? The critical values is by looking at numerator, which is 15 and 11 here. There's 4.25. So the critical value is 4.25. So step number 3, we have to compute the test value. The test value for F test is equal to variance 1 larger over the smaller variance. So 4.3 squared, since the given is a standard deviation, we have to square. And 3.6 squared, if we're going to plug in that one in your calculator, that is 1.43. In step number 4, we have to make a decision. Okay, we have to graph first. Okay. This is skewed. Actually, this is skewed. If we're going to graph this one, that's actually, we have to emphasize that this is skewed. So our critical value is 4.25. Okay. And our F value is 1.43. So therefore, this does not belong to or does not fall to the critical region. So we could not reject HOY since 1.43 does not fall in the critical region. So it does not fall in the critical region because this is our critical region. So the decision is to not reject the null hypothesis. Our step number 5 here is, since our H1 is our claim, so since the decision is do not reject the null hypothesis, we will start that there is not enough evidence. So we should know how to start with step number 5 in the summarize the results. Since our H1 is our claim and we did not reject the null hypothesis, so we'll start with a statement. There is not enough evidence to support the claim that the variance of the noise levels of the riding power mowers is greater than the variance of the noise levels of the push power mowers. Okay, so that's it on how to solve for problem number 4. Alright, let's proceed now with problem number 5. And problem number 5 is the p-value method. So let us have first problem. The problem states that the CEO of an airport hypothesizes that the variance in the number of passengers for American airports is greater than the variance in the number of passengers for foreign airports. At alpha 0.10 is there is enough evidence to support the hypothesis. The data in millions of passengers per year are shown for selected airports. Use the p-value method and assume that the variable is normally distributed and the samples are random and independent. So the first step in discussing this way is we have to state the null hypothesis. Our null hypothesis when you're comparing the variances is equal. The variance of 1 and the variance of 2 are equal, and our H1, it depends upon the problem, which is greater than the variance of the passengers. So our mu1, no, not the mu1, variance 1 is greater than the variance 2, which is our claim. In step number 2, we have to compute the test value. So in order to get the test value, we have to compute the variance of this one and the variance of this one. So using your calculator, and I believe that I have taught you in how to use a calculator during the previous discussion, so I'll just present to you the result of this one. So for American, so we have here, okay, so in each group we have, okay, our numerator is equal to our s squared 1. So for Americans, so the variance is 246.38. The other one, using your calculator during the foreign airports, so the variance is 95.87. So we have to know how to compute using calculator, because in this case, calculator is very important if the given are in raw data. We have to compute the variance. So from getting standard deviation, we have to square to get the variance. And also we have to compute using the mean. We can actually go immediately with our calculator. So the variance 1 is equal to 246.38 and the variance 2 is equal to 95.87. So now our F test is equal to, we have here the larger variance 246.38 over the smaller variance is 95.87. By the use of calculator, we have computed that 2.57 as our F value. Step number 3, we have to get the P value. How to get the P value? We have our DFN. Our numerator, the greater variance is here above, and our n here is 1, 2, 3, 4, 5, 6. So 6 minus 1, that's equal to 5. Since our numerator is the larger variance our numerator, the number of n in our numerator is 6 minus 1 to get the numerator, degrees of freedom of numerator. And also for our DFD, so we have 4 minus 1, the denominator, which is 3. And after which class, so we have to locate for the variance. So we have here 5 and 3. 5 and 3 is 5.31. So if that is 5.31, if we're going to observe here class, our alpha is equal to 0.10, 0.05, 0.025 using our table, 0.01 and 0.05. Since 2.57 are f value, that is, this is less than 5.31. If we're going to look at here, when the f value is getting smaller, the alpha is getting bigger. Or there is in inverse proportion. So we have here, when the f is getting smaller, the alpha is getting bigger. Right? Nagkasaka siya. So in this case, we have since 2.57 and our critical value here is 5.31, basing on but the p-value here, which is 0.10. So we could say that the p-value of 2.57, okay, the p-value of 2.57 is lesser than, since we got here from 0.10, 0.05. If we're going to look at it, the one in your table, there's 5 and 3, 5 and 3, 5 and 3 as RDFN and DFD. So 5 and 3, since our critical value is 2.57, we could say that the p-value is greater than alpha 0.10. Why? Once this is lesser, this f value is 2.57, which is lesser than 5.37, which is our alpha is 0.10. So it means that the p, if you're going to convert this one to 2.57, the result of this one is lesser or greater alpha compared of the alpha given here, which is 0.10. So therefore, if p-value is greater than the alpha 0.10. Let's go back here. Let's go back. Primer sub 10. Our f value is 2.57, and we get this numerator and denominator, degrees of freedom 5 and 3, and we get that the critical value is 5.31. If we're going to look at here, if you're going to look at the condition here, when the f value is getting smaller, the the alpha is getting bigger. Meaning to say, if the f value is if the f value is 2.57 is lesser than 5.31, it means that the p-value is greater than 0.10. So that's it, because that is inverse proportional. When the f value is getting smaller, the alpha is getting bigger. So the p-value here, so step number 5, the decision is not to reject the null hypothesis since the p-value is greater than 0.10. Why is it greater? Because that is beyond here, lesser, and also the alpha will become bigger. Okay, that's how to find. We have to get all the value for this one in order to compare with. And step number five, this is four. In step number five, we get a summary here. Since our claim is our H1 and we do not reject the null hypothesis, you will start with a statement: there is not enough evidence to support the claim that the variance in the number of passengers of the American airports is greater than the variance of passengers for foreign airports. Okay, that's it for problem number 5. So try this at home, try these two problems, and you have to submit that one during our class. And if we don't have a face-to-face class or we have online class, so by the next meeting or by next day of our class, first day of the week, you have to submit that one in our office. So thank you so much for listening and God bless everyone.